Hey everyone, this is Dr. Walker. In this video, we're going to go over another example of finding the electric field due to a continuous charge distribution. This time it's going to be a ring of charge. Let's take a look. We're trying to find the electric field due to this ring of charge at point P. We're told that the ring has a uniform charge density, lambda. Let's also say that it has a radius r, as we can see in the picture. And let's just say that it also carries a total charge Q. That will just simplify our answer, make it look a little bit prettier. So we know that to solve problems of finding electric field due to continuous charge distributions, we need to find an expression for dE, the field due to a very small charge element, and then we need to integrate over the entire charge distribution. So let's do the same thing that we did in the previous example, and that is, let's look at a few elements, charge elements, to see if there's any symmetry in this problem that can help us simplify the problem. So let's consider a dq over here at the top, and the electric field, and let's consider it positive charge element. The electric field would point away from it. This would be dE. Let's call it dE1 due to Q1, dQ1. And let's say we have another charge element at the bottom here, dQ2, then it would produce an electric field away from it in this direction. So it looks like there is some symmetry, just like in the previous problem with the rod. It looks like all of the downward components will be canceled by the upward components. But what about if we have an element over here, let's say on the front side of the ring here? It's a little bit harder to draw, but it would have an electric field kind of pointing away. And then an element from the far side here would have an element pointing towards us. So once again, there is a component. Before I called it the downward component, but now I can call it the near one and the far one that cancel out. So that component that's canceling out is the component that is perpendicular to the x-axis. Only the component parallel to the x-axis is not going to cancel out. So that's the first step. See if there's any symmetry so that we know exactly what dE that we need to solve for. In this case, we're going to have to find dEx. So let's erase all of this extra stuff here so we don't have a mess. And let's call this dq. And let's draw a dashed line from dq to this point P. It will be at a distance r. And let's go ahead and write what we're looking for. We're looking for dEx, the x component, which is along this way. And so let's define an angle theta over here so that our dEx over here is going to be use the cosine because it's adjacent. So dEx equals ke dq over r squared cosine theta. Now we need to figure out what variable we're going to integrate over. In the rod problem, the previous example, we were integrating along the x direction. But here we see that all of these charge elements, they have the same distance x to point P. So we're not integrating along x, we're not integrating along r. All the points also have the same distance r to point P. So what we can consider is we can consider that one of these elements has a length dl, and that we need to integrate this dl across the whole circumference of the circle, which is 2 pi r. Or another way to look at it is we can consider that this dl here has a little angle phi. And it's very common whenever we have a circle to rewrite dl as the radius times d phi, right? Because this is the definition of arc length, right? The arc length L is r phi, so dl is r d phi. So if we rewrite the length element dl as r d phi, then we can think of integrating phi from 0 to 2 pi, integrate over the whole circle. So different way to look at it, you can integrate over dl over L or phi. I'm going to choose phi. Now it's time to rewrite our variables. We're going to write dq as lambda dl. We don't need to write it as dx this time because we're not integrating over x. And then we're going to write dl actually as r d phi. So let me actually rewrite it as r d phi. Now, cosine theta and r squared, those are actually constants as well, right? The theta is the same for all of the points. The r is the same. We still need to rewrite these two in terms of the variables that were given in the problem, but we're not going to be integrating over these expressions. So just like in the previous problem, we can write cosine of theta as being equal to adjacent over hypotenuse, and the r is the hypotenuse, so square root of x squared plus r squared. So we can go ahead and rewrite cosine as x over square root of x squared plus r squared. And we can go ahead and substitute all of this in here. X over square root of x squared plus r squared for cosine phi. And then the r squared here is going to be x squared plus r squared. And now we can go ahead and simplify a little bit. We're going to have ke lambda r x over x squared plus r squared to the 3/2. So this part here, the x over the x squared plus r squared to the 3/2, that looks like what we were integrating over in the rod problem. However, the x is constant in this case, so all of this is constant, and we're only going to integrate over phi, so it makes this problem actually a lot easier than the previous one. So now we're ready to write the field as all of this expression, which is a constant, and we're going to integrate phi from 0 to 2 pi, which will give us 2 pi. Again, you could have integrated dl from 0 to 2 pi r if you wanted to, you would get the same result. So in this case, we're going to have ke lambda r x 2 pi over x squared plus r squared to the 3/2. And then the final simplification that we can make, because I mentioned that we could say that there is a total charge q. Well, we know that the linear charge density is q per L, where the length here is the circumference, and the circumference is 2 pi r. So if we look at our answer here, we do have a lambda right here and a 2 pi r, and that is equal to q, right? Q equals lambda times 2 pi r. So what we can do is we can rewrite this as q to get ke x q over x squared plus r squared to the 3/2. And let's not forget a direction. We said that the electric field would be in the x direction, so we can just say I hat. So this is the expression for the electric field due to a charged ring, and we followed the same steps as finding the electric field due to a charged rod, which is to rewrite dq in terms of the variable that we're going to integrate over and make sure that everything else is a constant. so that it can come out of the integral and integrate over 5 from 0 to 2 pi, and that is how we got our answer. We still have another example coming up, so please join me for that one.